How is everybody today? How was the weekend? Was the weekend, no? Not so good? Oh, yeah. So, by way of announcements, before we get into today's lecture material today, by popular request, those of you who have demos, Aaron has very kindly agreed to allow some demonstrations to occur on Friday for the labs. So if you're having some... No, it's okay. You can applaud if you like. If you're having some trouble getting the lab together for your appropriate date, then Friday is an option. Please try to get it done for the regular due date, though, because I have a feeling that this will turn the Friday section into a zoo. So, you know, so be it. Anyway, so that's all I have in terms of announcements. So, we were talking about operational amplifiers. So, applications of operational amplifiers. Where would you use one? Anybody? Oh, this is going to be a good class.
Lab 4.
Lab 4, yeah, okay, sure. But in what context? Why would you add one to a circuit where one wasn't before? What is the purpose of them? What is even the point of this? Yes?
For signal conditioning.
For signal conditioning, yes. So, with many different types of things you may wish to read signals from, you can have a couple of different situations. One, the information contained in that signal might be in such small increments, such small fractions of a volt, that it's not, you can't really pick it up with your analog to digital conversion, right? So this would be an application where you need amplification, right? You need to amplify the signal. Another situation in which you would use an operational amplifier is if the thing you were reading the signal from had too high an impedance for you to get a good reading off of it because it has a very low slew rate. Obviously, in order to read electrons, you must get enough electrons to be read, right? Some types of sensors provide so much impedance, in particular piezoelectric, but there are others, so much input impedance that it can be difficult to get a good reading off of them. This is another situation in which you would want an operational amplifier. Good. Any questions so far? Good. So, we had talked about a couple of things with these. So your ideal op-amp, where is it here? There we go. So when you're conducting circuit analysis on operational amplifiers, there are two OpAmp laws, I guess you could call them. These are approximations which assume that the operational amplifier works precisely and exactly as it's intended, with no additional complicating factors, which of course can't possibly be the case. As we're going to see over the course of this lecture and next, operational amplifiers do have, they do not follow these laws perfectly, but this is sort of the intent, and normally they operate well enough that you can hold these two laws to be true for the purposes of circuit analysis. So, for analysis on operational amplifiers, the voltage at the input leads are equal. These are operational amplifiers in feedback configuration. So, positive, negative, in ideal circumstances and for the purposes of analysis, you consider Vin to be equal, or Vin to be VIP, because it's negative and positive. V plus and minus would also work here. The other assumption that you make is that the current through either input lead is 0. So we assume that the input impedance here is sufficiently high as to all but block the flow of current. This, of course, isn't quite true, but it's true enough for us to be able to perform approximate analyses. Good. So, one thing that perhaps we should note before we go on, reiterate, the gain on an operational amplifier, if you use it in open loop mode, so if you don't connect any feedback into the operational amplifier, the gain is quite large. It can be in the like 10 to the 6 to 10 to the 9 range, which is just ridiculously huge. So we're talking about, you know, in the case of 10 to the 6, a microvolt turns into a volt through an operational amplifier without any feedback. So this is why we typically do feedback, because, you know, factors of 1,000,000 or 1,000,000,000, while cool on paper, are far less practical than scaling factors of 3 or 4 or 10, or even 1,000 is a lot more practical. Good. So, good. So let's dive into this circuit here. We're going to analyze this circuit. This is a current amplifier. So rather than amplifying voltage, as we saw previously, this is a circuit which provides more current at a particular ratio. As we're going to derive, that ratio is 1 plus the value of the feedback resistor, RF, over the value of the ground-connected resistor, R. Good. I'm going to do it in the middle, because I think I had a complaint last time that it was like off to the one side and people couldn't see it. So, screen up. Projector off. Good. So this is what we had. That's the load. So this circuit is in kind of a weird configuration with like this guy going up off over the side. So if we were to rewrite this thing so that it's slightly more, you know, what we might expect to see, we would get something like the following. That'll be good enough. right? You just take it, whip it up to the other side. Makes a bit more sense, I think. So, our first observation. Well, let's first label these and then we'll make some observations. So we've got voltage at the negative and positive leads. We've got labeled points A and B, which of course will also have corresponding voltages VA and VB. So, what's our first OpAmp law again? Oh wow, this is really going to be a good class. First OpAmp law.
The voltage of both inputs are equal.
Yes. V plus is equal to V minus. Second one, of course, is going to be that there's no current flowing into either of these leads. So, what does that say about the current traveling along this branch of the circuit? We'll call this I1. None of it flows this way. So this is one current. What do we have along that branch of the circuit? Well, yes, we do have a resistor. But we also have current source, I in. All right? So we can say with certainty that I1 is equal to I in. Right? Make sense? Because there's nowhere else for it to go. So, let's focus on this point now. We also have, let's say, I2 and I out. So, we can very quickly and easily determine that I out is equal to I in plus I2. Right? So, I out must be greater than I in, so this is a current amplifier. The only question is, how much is I2? Right? Good. So, now we can start applying some voltages. So, for this I2, we know that I2 is equal to the voltage at point B divided by the resistance R. Right? So, we can almost immediately sub that in. What we want, though, is we want I2 in terms of I in, right? So, we can also state with confidence, because of Ohm's law and stuff, that VB minus VA over RF is equal to I in. Right? Potential difference across this resistor divided by the resistance of the resistor is equal to the current. Ohm's law. So, we can then okay, so a couple of other observations, however. So VA is equal to V negative, right? V negative is equal to V positive, and V positive is connected directly to ground. So we can actually write out that term entirely, right? Because of the OpAmp laws. Yeah? Any questions? Good. So, we can then say VB, of course, is equal to IN, which I know at times RF. I know you could have gotten there just straight from Ohm's law, but good. We then take this guy and that guy, and we can say I2 is equal to RF over R IN. Sub that guy into this equation. I out over IN is equal to 1 plus RF over R. Make sense? I'd like to bring the board down, so is anybody still writing this down? Out come the phones. Good Lord, the age we live in. So, we're not going to do an analysis of this one, but there we go. So, that was the current amplifier. In situations where you need to amplify a current source, that's what you use. The voltage follower has a output voltage which is equal to its input voltage, right? So it should be reasonably easy to determine why that might be the case if we think about the OpAmp laws, right? Number one, this voltage is equal to that voltage. Number two, no current flowing, right? If there's no current flowing across the resistor, then there's no voltage drop across the resistor, which means that the input voltage here is equal to V plus, which is equal to V minus. There's no current coming here, so it's equal to V out. So what is even the point? Very high input impedance, but very low output impedance. Almost unity gain, not quite unity gain, as we're going to see in the following slide. Very close to unity gain, but this is an impedance. This is for impedance signal conditioning, right? Again, if you need to read a piezoelectric crystal, you will need something like this if you want to get anything meaningful. So, suitable for high output impedance sensors such as piezoelectric devices. If we were to break this down in terms of its equivalent circuit, just reminding ourselves that we have our input impedance and our output impedance here, where Zi is something like 1,000,000 ohms and Zo is something like 100, right? If we were to take these resistors out of that and sort of spread them across one circuit, this is what we would get. So, in this case, Vi is equal to Vi prime, which is the voltage across this input resistor, plus K times Vi prime. Vo is equal to K times Vi prime, because that's what op-amps do. Vi, therefore, is equal to 1 plus K Vo, which means that Vo over Vi is K over 1, K plus 1, right? Which is very nearly 1, but not quite 1, right? Very, like, this is what is meant by near unity gain. So in this case, do we get slightly more or slightly less amplification than we wanted? Eh? Less, yes, because that's how fractions work. Good, good, good. So, here's a question. Consider the temperature sensor signal conditioning circuit below that is supposed to implement a low-pass filter with 3 times gain. What is the problem with it? Anybody?
Should the R3 or R30 be on the bottom of the branch instead of on the top?
Yep.
Well,
That's.
Oh my god.
Yep. Or another way to say that, you should move this connection to the other side of it. Yeah, so if you compare to our voltage amplification circuit, notice that the resistor needs to be between ground and the amplifier, right? So that's that in this particular circuit. The fact that this has been wired incorrectly means all the way up to here we have a grounded voltage state. There's no current flowing here, right? So this is also grounded, which means that this is also grounded, right? So the whole thing would just, like, wouldn't do much, basically. But yeah, good. So, if we have an operational amplifier which has one lead connected to ground, we call it a single-ended amplifier. This is actually not like, one makes circuit analysis somewhat easier. This is not actually a terribly useful thing to do in practice due to an effect called ground loop interference. So, an interesting effect. A lot of people think that ground is just ground, right? It's just, it absorbs all of the electrical energy and nothing is like, you know, it's just ground. You don't have to think about it. However, it turns out that ground is not as easy and uncomplicated as it first seems. We're going to have a few slides on this coming up, but essentially, you can have frequency signals which pass through the ground wire in a circuit and sort of fluctuate and throw things off and cause noise and interference. And operational amplifiers, like the whole purpose of the thing, is conditioning signals. So if you're allowing other signals in to interfere with how your op-amp is amplifying things, then you could, with one of these things, be amplifying, for example, the 60 hertz oscillation that comes native with any household electricity service, right? So, the solution to this problem is what's called the differential or double-ended amplifier. So, previously, we had this guy just connected to ground, but now we have 2 input voltages, resistors on either side, right? And our output voltage is related to the input, or the difference between the 2 inputs, by a factor of RF over R, right? So, I hate these things. So yeah, let's analyze that circuit. Da 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 bum bum. You've won math. Da It's supposed to go past, but okay.
There's a barista shop.
Oh, yeah, that would do it. Okay. No wonder these things break. Jeez. That's okay. That's maximum lowness right there. All right. So, our circuit. We have V1, V2, incoming input leads. Both of these have a resistor on them with a value of R. We'll have voltage point A and voltage point B, mostly just so that we can say that A is equal to B. A resistor with the same value as the feedback resistor connected to ground, and a feedback resistor thusly. VO. Wow. VO across those two. Okay. Good. So, let's label some currents. Call this I2. We'll call that guy I1. Which we will also call IF for some reason. There we go. Just to say that they're equal later on. I think I got it. I think I got it correct. Here? Oh no. Alright, well, anyway. So I1 is equal to V1 minus VA over R. So, voltage across this resistor, V1 minus VA over R. I2, same procedure. V2 minus VB over R. IF, I guess it is. I shouldn't second guess, I should just follow the freaking thing I wrote out. I feedback, which, looking at this and remembering our OpAmp laws, we should begin to instantly think that there might be some kind of relationship between I1 and IF. So, we of course know VA is equal to VB. So, because of that fact, we know that I1 can be rewritten as V1 minus VB over R, and IF is equal to VB minus V out over RF. Basically just take all the A's and change them to B's so that you can then collect them and destroy them later on in the process. So what is this VB right there? So assuming that no current is going into that op-amp, what does that look like to you? Because we've seen these before. most recently with potentiometers. We have a term for this. What's it called? Voltage divider. Thank you. So VB is equal to V2 times RF over R plus F. There you go, because it's a voltage divider. Okay? I mean, you can derive it each time if you like, but, you know, there you go. So, from here, we notice that we have two independent voltage sources, V1 and V2. Our next step is to perform circuit analysis using superposition. Superposition. So, holding V2 equal to 0, we can then immediately derive that VB is equal to 0, VA is equal to 0, and from this we can conclude the I2 current is equal to nothing. I2 is equal to 0. No voltage, no current. If you don't work, you don't eat. So, I1 is therefore equal to V1 over R, because, you know, VA is now ground, right? We can also say IF is equal to negative V out over RF, because remember what happens when you've got the one of these connected to ground, right? The current will continue to flow because it's got nowhere else to flow, right? Past the point where it's ground, and it'll generate negative voltage on the other side, right? So the voltage across the resistor RF might be, it'll be the reverse of what you think it is. So, since we know that I1 is equal to IF, we can say V1 over R is equal to negative V out over RF, which means V out A is equal to negative V1 RF over R. So much for the easy one. Our next step is to hold V1 equal to 0. So, B holding V1 equal to 0, we can immediately state that VB is equal to what we found it to be before, V2 times RF over R plus RF, which is also equal to VA. Yep. So, V1 over R minus VA over R is equal to VA over RF minus V out over RF. So, that's derived just from, again, the observation of I and IF being the same, and taking the denominator and splitting it across this, like separating those two terms out. So this guy, we can immediately write that off as being equal to 0 because, of course, we are holding v1 equal to 0, right? So we can rewrite this. VA over R plus VA over RF is equal to V out over RF, which, of course, we got to collect these terms, right? So RF VA over RF R plus R VA over RF R is equal to V out over RF. Can I just continue over here? So collecting these terms, we can say VA times R plus RF over RFR is equal to V out over RF. And we can cancel these terms. So, in the end, we can say that V out B is equal to VA times R plus RF over R. There we go. Sorry, 2, 1. So, good. Of course, we don't need it in terms of VA, we need it in terms of V2, right? So, we can pull in our previously defined relation, right? To say that this is equal to R over R plus, RF, there we go, plus RF over R, V2, right? Cancel this one, cancel that one. So it's equal to RF over R, V2. Via the superposition principle, V out is equal to V out A plus V out B, there we go, which is equal to V2 RF over, what the heck is going on there, you? RF over R minus V1 times RF over R, which of course, if you collect it, is RF over R V2 minus V1 differential amplifier. Amplifies the difference of the two signals. Yeah? There we go. Or attenuates, but why would you want it to attenuate? Well, you might want it to attenuate. Okay, good. Any questions about that long and complicated derivation? Do you guys need a moment to capture it with your cell phones before I bring the board back down again? Good? Good. Good. Okay. No. So, why on earth would we use differential amplifier configuration? Aside from the fact that if you've been paying attention, you may recognize the term differential amplifier from our discussion of comparators, right? The core of each of the comparators that we were using inside of our analog to digital converters used a differential amplifier. So, single-ended configuration suffers from what's called ground loop noise. Ground noise in a ground noise in single-ended amplifiers can be eliminated with a differential amplifier. So that's one reason. So let's talk about common mode noise. So these guys, this is another way in which operational amplifiers are not as ideal as specified. So in an op-amp, it turns out that if you take the two leads of an op-amp, connect them together and connect them to some voltage source, like so, you will detect some noise. They will, like these things, in theory, there should be no output, right? Because the operational amplifier amplifies the difference between the two signals. They are actually being held down together instead of just being approximately together as we normally assume with operational amplifiers. So in this configuration, you end up with what is called common mode noise. It's called common mode because both of these input leads are connected to a common source, right? So, I had like a piece of skin on my lip which had caught the mask fabric. Disgusting. I'm going to be really happy when these things are gone. It's going to be awesome. Because they're just such a pain. So, anyway. One of the, so it turns out that the gain that you experience from an operational amplifier is not just the gain you want, but also this other common mode term, right? So what we want, ideally, is an operational amplifier which has a high degree of common mode rejection. CMRR stands for common mode rejection ratio. The common mode rejection ratio is the common mode gain over, it's the regular gain over the common mode gain, right? So the gain itself is the sum of those two terms, right? So what we actually have in an op-amp is we have the output voltage being equal to K times the difference between the two leads, plus the common mode gain multiplied by half the difference of those two leads. So both of these terms are there. The degree to which this term is there throws off the ideal of the amplifier. Ideally, we want this gain to be as close to 0 as possible. Now, it's not going to be. It's much, much, much less than the regular gain, but the regular gain is in the in the millions or billions. So these the common mode gain is only in the tens of thousands. So that's quite a bit less substantial than the regular gain, but still what's important is the ratio between the two of them. So the common mode rejection ratio is actually measured in decibels. You guys have done decibels a little bit? How many people know what a decibel is? How many people do not know what a decibel is? A couple of people. All right. So They're not that difficult to understand. For those of you who haven't heard of decibels before, have you done things in logarithmic scale? You know what I mean when you say that? When I say that, thumbs down if you have no idea what I'm talking about. Okay. All right. So with a logarithmic scale, you know, something like the Richter scale, which is for measuring earthquakes, each full value on the Richter scale actually represents an increase in the magnitude of the event by a factor of 10. So, you know, it's like 10 to the 10 to the 10 to the 10 to the logarithmic scale, right? Decibels are this, but then to a different decimal place, essentially. So we take the logarithm of the gain, right? Or the ratio between the regular gain and the common mode gain. We then take the base 10 logarithm of it to extract what the exponent would be, and then we multiply by 20, right? This is lots and lots and lots of things are measured in decibels. Normally you include decibels as the unit. It's very, very frequent in signal processing. You'll see decibels because filters have the characteristics of rejecting frequencies with frequency amplitudes with a certain, on the same idea. Generally speaking, with a filter, the point at which the filter rejects a frequency at a rate of -3 decibels is considered the cutoff frequency of that filter. Anything beyond that is considered to be too weak to be considered. So, get out of here. Go have dinner.